Good morning to all. Uh, Today we will be discussing on module 2, that is on lattice vibration. So in the lattice vibration module, we mainly discussing about vibration of monoatomic and diatomic lattices and quantization of lattice vibration, inelastic scattering of neutrons, and Einstein and Debye model of specific heat, then thermal conductivity, and we'll also discuss about what is the effect of imperfection towards lattice vibration of a molecule. So first of all, we'll just see what is lattice vibration is all about. Lattice vibration means, as you already know, it is actually vibration of atoms in a particular solid. Okay, so our entire discussion is mainly on the different properties of solid. Okay, and in that solid, if there is a vibration of atom happens. Okay, so the discussion will be on vibration of atoms in solid. Okay, so vibration of atoms in the solid, and we normally see that we know that lattice, what is lattice means? Lattice means a periodic arrangements of point in a space, that is we already have discussed. And we know that lattice plus basis means atom or a group of atom, so which constitute a crystal structure. So within a crystal structure we have a lattice, we have a basis. So when there is an atom which is placed in the lattice point, which will be started vibrating, and the vibration can be treated as a simple harmonic motion if uh, temperature is equal to 0 Kelvin. That is about absolute temperature. We can see that the energy will be minimal in that condition, and you can also see that the vibration will execute a simple harmonic motion. Okay, so the vibration of atom in solid at t equal to 0 Kelvin will be a simple harmonic motion, SHM. Okay, whereas in other temperature, okay, t not equal to 0 Kelvin, if the temperature, if we increase the temperature fluctuations will be there, then there will be energy fluctuations will be there, so it will execute an harmonic motion in that scenario. Okay, so we have two kind of motion we can expect with respect to temperature. When t equal to 0 Kelvin, we have a simple harmonic motion. When t not equal to 0 Kelvin, we'll have an harmonic motion. So we can see that if you particularly consider a lattice like this. Okay, and we have atom which is placed on this lattice, and this particular atom is started vibrating in this crystal structure. So we can see that when particularly if you consider a single atom, okay, a single atom, if you consider, so we are considering one single atom, and which has three modes of vibration corresponding to that. And now if you consider n number of atom, okay, then it will be having 3n modes of vibration will be there corresponding to that. So we can actually consider a single atom has three modes, right? Three modes means it can vibrate in three different directions. So in that perspective, one can actually say that three modes corresponding to it is actually a three-dimensional vibration, where one atom having three modes, which is having a three-dimensional harmonic oscillator. We can actually treat as a single atom which is having three modes, which is vibrating like 3D harmonic oscillator, like we can actually consider. Okay, because it's having three-dimensional harmonic oscillator like. And now we can also see that when you can say a vibration is simple harmonic motion, a vibration is said to be simple harmonic motion when the force is proportional to x, where x is the displacement or the distance by the vibration is actually, for example, if this atom, this particular atom is started vibrating, it's slightly moving at position by x distance, and correspondingly there will be a change in force as well. You know that F is equal to kx, so which is like minus kx, which is actually Hooke's law. Okay, so a motion to be simple harmonic motion, so the force should be proportional to x, and that is it should execute a Hooke's, it will follow a Hooke's law. And also you can see that the potential energy is proportional to x square. Okay, the potential energy is proportional to x square, you can see. So for a simple harmonic motion can only execute, the force is proportional to x and the potential is proportional to x square. And now in our anharmonic situation you can consider that the force may not be equal proportional to x, and u may not be proportional to x square as well. Okay, so it is a condition for enharmonic motion. Okay, and now we can consider why lattice vibration. So when you consider the properties of a solid, why lattice vibration is more important. The lattice vibration is more important because the lattice vibration decides, the lattice vibration decides different properties of a solid, like thermal properties of a solid. Okay, and it will also decide the property optical properties of a solid. Okay, and it is also decide the mechanical property. So different property like thermal, optical and mechanical properties of a solid is decided by the lattice vibration, how lattice is getting vibrating, how whether it is a periodic, whether it is executing a simple harmonic, whether it is executing an enharmonic motion. So this is an important factor when you deciding the thermal, optical and mechanical property of any particular system or any particular solid system. Okay, so as I said, we have a lattice, as we can see that here, we have a lattice, right? So this lattice actually we can actually connect like a spring. Okay, so this there is a lattice distance is there, so this lattice actually you can actually mimic like an elastic spring. So this particular lattice structure, so you can actually mimic like a elastic spring because it has a regular arrangement. Lattice means it's a periodically regular arrangement, you can see. So their atoms are joined by elastic spring, so you can assume like that. So you can see that when you heat a particular conductor wire, okay, so the heat will conduct fast from one point to another point. And wherever you consider an insulator case, the heat will move very slowly. So that is, you know that very good metal is a very good conductor where heat can conduct very fast, and whereas in any insulator, any bad conductor will slowly will conduct the heat, because the vibrations of atoms are coupled in the case of insulators. Okay, so basically if there is a vibration happens, for example I am just putting a force over here, so this will be started vibrating and that vibration will be transferred to the next one, and the vibration will be transferred to the next one. So it will keep on transfer the vibration to the neighborhood one. So one, if you, even if you are giving a simple force to a particular one, sorry, so you can actually transfer that vibration to the neighborhood ones. Okay, so when you consider the amplitude of vibration, so when you consider the amplitude of vibration means, so that will be proportional to x. Okay, so when you consider the amplitude of vibration or the force, so force is proportional to x in the case of a simple harmonic case. So I repeat, so if you have you can actually consider two atom is connected like a elastic ring. So it was an assumption by uh, uh, for for us, and we also see that for a simple harmonic motion, f is proportional to x and u is proportional to x square, and this you can actually see at a very low temperature. Okay, so t is equal to 0 Kelvin, I said. So at very low temperature you can actually see this scenario because their thermal fluctuations are very low, so the atoms are be much more stable. Okay, So when it comes to high temperature, there will be larger vibration. So it will be executing a anharmonic vibration in that scenario. Okay, and also another point is that at a low temperature there will be no thermal expansion. Okay, so no thermal expansion as well. Okay, so in simple harmonic motion, if the atom is executing a simple harmonic motion, and there will be no thermal expansion as well. If there is no thermal expansion, okay, if there is a thermal expansion, then there will be no simple harmonic motion. Okay, in the absence of thermal expansion only, there will be simple harmonic motion will be executed here. So here, in the another point, we said that the motion of each atom, the motion of each atom is actually coupled. So if any vibration to a single atom will be transferred to the neighbor one. So it will share by the each atom, and all the atom will be getting vibrating in that scenario. Okay, and we can see that initially the atom will be vibrating with their normal modes, that is due to their internal energy, and this type of vibration is the main reason for the thermal property of a solid, like specific heat, thermal conductivity. This all depends upon the uh, free vibration of atom with their normal modes. Okay, so that is the reason. So this is the primary reason for the thermal property. Okay, thermal property, especially specific heat and thermal conductivity. Okay, thermal conductivity of solid. Okay, so free vibration of atom with its normal mode is the main reason for the thermal properties like specific heat and thermal conductivity of solid. Okay, and this actually free vibration means we are not applying any external force. Okay, so the atom is freely vibrating with their normal modes. Now if there is a scenario, if we are applying an external force, okay, so you are applying an external force to the lattice or crystal. Okay, so it will also experience a vibration under some external force. So this force can be two type. This external force can be two type. One can be mechanical, another one which is electromagnetic. Okay, so there is two type of external force can be also you can apply for lattice vibration. If it is mechanical, so you will be getting acoustical properties like to sound or optical, and here you can actually get optical properties. Okay, acoustical means it's also mechanical property. Okay, so by applying mechanical force you can actually see the mechanical property. By applying electromagnetic force you can actually see the optical properties of a solid. So in this scenario you are actually applying a forced vibration, right? So you are actually applying an external force over there. So now if we incident a sound wave is a longitudinal wave, then this atom can vibrate along the direction of that wave propagation. So the sound wave can only generate one mode. Okay, uh, sound wave is a longitudinal wave. So it will, if you vibrate an atom with a sound wave, so the direction of propagation will be along the direction of wave. Sorry, direction of vibration will be along the direction of wave, and the sound wave can only generate one mode in that case. Now if you consider, or like if you have a sound wave, okay, so sound wave to a solid, okay, so it will be having a single mode, because it is having a the lattice vibration will be along the direction of propagation, so it will be a longitudinal wave as well. So that is, you already know it's a longitudinal wave, sound waves. And now if you have an electromagnetic wave, so you are trying to send an EM wave to a solid, okay. And EM wave, you already know that electromagnetic waves are transverse electromagnetic waves, so those are transverse waves, okay. So in transverse wave, the atom will be vibrating along perpendicular to that. So the vibration will be perpendicular to the direction of propagation. So in that case, you can actually get two modes of vibration will be there. Okay. So there will be two modes of vibration if you are sending an electromagnetic wave. Okay. From this case, you can actually obtain, as I already mentioned earlier, you can actually collect the optical properties of that particular solid by sending an electromagnetic wave to a solid. Okay, so it has two modes of vibration, whereas if you send a sound wave, since it's a longitudinal wave, the atom will be vibrating along the direction of propagation, so you will be only getting single mode. In electromagnetic wave case, the atom will be vibrating perpendicular to the direction of propagation, so that you will be getting two modes of vibration in the case of electromagnetic wave. And this vibration you can actually utilize to understand the optical properties of solid. So I'm not going very detailed about how you can identify the optical properties and all, so that we will be discussing later on the session. Okay, so at this part, up to now we have actually focused on the basic aspect of lattice vibration. What is lattice vibration, and how a lattice vibration will be a simple harmonic, or it will be anharmonic. What are the condition, what are the, if you have a free vibration with the normal modes, and there will be external force you can apply like electromagnetic or mechanical, and what will be the resultant one, and what are the properties you can actually collect it from that. Now I'll moving on to discussion of okay. So we'll just discuss about vibration of one dimensional, okay, vibration of one dimensional monoatomic monoatomic solid. Okay, so we'll just discuss vibration of one dimensional monoatomic solids now. Okay, so now for a one dimensional monoatomic solid, so let us consider we have a one dimensional chain of atom. Okay, so we have a one dimensional chain of atoms, and which is having a mass m, and which are connected to the an elastic spring of spring constant c, and the distance between two atoms we consider as a, where a means the lattice parameter as well. Okay, so you can see here how it comes here. Let me bring a picture here. Okay, so we'll discuss vibration of one dimensional monoatomic solids here. So as you can see here, we are actually considering a one dimensional chain of atom which is having a mass m, as you can see in the figure, and which is connected by an elastic spring of spring constant c, and the distance between two atoms is specified as a, I already mentioned. So as you can see, this is a equilibrium vibration on the top of the figure, and you can also see that under the vibration the initial position of atoms are slightly displaced, you can see, So you can see that un minus 1, un minus 2 is a different positions regarding that. Okay, n minus 2 atom, n minus 1, nth atom, n plus 1th atom. So there is a slight displacement you can see under the vibration of atom from the initial position. Okay, so this can be either left or right, so that depends upon the vibration you are applying. Okay, from the direction of vibration you are applying, force you are applying. So under vibration, so it's executing a motion. So what we are supposed to do is that what is the different kind of parameters that is connecting to this. So when you consider one dimensional diatomic case, what are the parameter we need to consider? Where un minus 2, un minus 1, un plus 1, which specify the position, okay, of different atom at different point. What is the position of nth atom under the vibration? What is the position of n minus 1th atom under the vibration? So that is the un minus 1, un minus 2 are specified. Okay, so now we just consider the equation of motion by considering the neighborhood atom. Okay, by considering the neighbor atoms only. Okay, you can also say that that is nearest neighbor. Okay, so nearest neighbor only. So we can see that since we consider that the motion executing a simple harmonic motion. Okay, so if it is executing a simple harmonic means f is proportional to x and u is proportional to x square, and it follows Hooke's law. Okay, Hooke's law. Okay, and according to Hooke's law, f is equal to minus kx. Okay, or rather if you want to simply represent, you can actually also represent as f is equal to kx, where x means it is a displacement from its mean position. Displacement from mean position. So you can actually say this equation f is equal to, so where k എന്ന് പറയുന്ന spring constant ആണ് നമുക്ക് പറഞ്ഞിട്ടുള്ള we actually seen in this figure that spring constant is what, spring constant എന്ന് പറയുന്നത് c ആണ്. So you can actually represent as c un plus 1 minus un minus c into un minus un minus 1, where c എന്ന് പറയുന്നത് I already say that is spring constant. Hooke's law പ്രകാരം k ആണ് spring constant. നമ്മൾ ഈ particular കേസിൽ we are actually considering c as the spring constant, and this particular term actually representing displacement of nth atom from n plus 1th atom. Okay, so we are considering the neighborhood one, and now by considering this particular equation, this equation you can either write as c into un plus 1 minus 2 un plus un minus 1. Okay, un minus 1. Okay, so keep it as equation number 1. Okay, so now we say that the atoms are performing what, simple harmonic motion. So it is executing a simple harmonic motion, and their displacement will be also simple harmonic in that case. So we can actually write the displacement in terms of simple harmonic wave. Okay, so we can actually write this displacement in terms of simple harmonic wave. Okay, so simple harmonic wave means it's actually executing a sinusoidal wave. Okay, so we have a sinusoidal wave like this. Okay, so it's executing a sinusoidal wave of equal amplitude, and you can see that this particular point is our a in that scenario. Sorry. Okay, if I mark this particular distance is our a. Okay, and you can actually see that this simple harmonic wave will be un is equal to u0 e raised to I omega t minus kx, it will come. Okay, so here you can actually represent this equation as like this, and here u0 is an amplitude of this particular wave, and omega is the frequency. Okay, angular frequency or frequency of vibration. Okay, frequency of vibration, and k is the wave vector, and x is the direction of propagation. So this x actually I can replace as Na. N is the number of atom, nth number of atom. A means the lattice parameter. Okay, so for example, if I say that the solid start its vibration from first atom at a distance a, and second atom will be, so it will be a, Na will be a, and second atom will be, it is 2a, and third atom will be 3a, so it goes on like that. Okay, so you can actually say that it will be 1a, 2a, 3a, so it's the first atom, second atom, and third atom. Okay, where a is the end, the value of n will vary from 1 2 3. Okay, so n has a value will change like that. So you can actually see that simple harmonic wave will be having un u0 e raised to I omega t minus k, where k is a wave vector, omega is the angular frequency, and this x equal I can actually replace as what, u, when u0 e raised to I omega t minus k kna kna. Okay, so it will be kna, and that un plus 1, so un plus 1 becomes what, it will be u0 e raised to I omega t minus k into n plus 1 a. Okay, and un minus 1 you can actually write it as u0 e raised to I omega t minus k n minus 1 a. Okay, and this I can write like un e raised to I k minus la. Okay, minus I k a, and this also I can write as un e raised to plus I k a. So if you can just expand this term, expand it again, you can actually write this term as u0 e raised to I omega t minus k n a plus k n, and now then you can actually make it like this. Okay, so now if you put this equation into the previous one, okay, previous one means first equation. What is the first equation? The first equation was f is equal to c un plus 1 minus 2 un plus un minus 1. So if you substitute un plus 1 in that equation, un in that equation, and un minus 1 in this particular equation. Okay, so if we substitute in equation 1, so then you will be getting us that f you can actually convert as m d square u by, okay, un by dt square. So it's like normally dx by d square x by dx dt square, f is equal to ma in that equation. So c, you can actually un you can take it outside, so it will be having e raised to minus I k a minus 2 plus e raised to I k. So you can just try substituting and you can actually get this relation. So c into, okay, it will be not small c, it's capital C. Okay, cu1 e raised to minus I k a minus 2 plus k will become, and this m d square un already you know, that is u0 e raised to I omega t minus k n a എന്നുള്ളതാണ്. So if you put that into this equation, and if you take the second derivative of that equation, you will be getting as minus omega square m un, that is equal to cun into e raised to minus ika plus e raised to ika divided by 2 minus 1 into 2 will come. Okay, and that implies you can actually cancel un and un here. Okay, so you'll be getting omega square is equal to minus 2c by m cos ka minus 1 will come. How cos ka? Cos ka because you know that e raised to I theta. So there is an equation like e raised to minus I theta plus e raised to I theta divided by 2. That means cos theta. So it's a relation that is you already know. E raised to minus I theta plus e raised to I theta divided by 2. That is cos theta. Here theta is Ka. So you can actually get cos Ka minus 1. So you'll be getting this equation like this. Okay, and there's also a minus here, so this equation omega square you can actually write as 2c by m 1 minus cos ka. So if you multiply this minus into this bracket, so you'll be getting 1 minus cos ka. Like that you can get this solution. Okay, and you can also make this equation, you know that cos ka you can actually write like 1 minus 2 sine square ka by 2. So this is actually we just making for our convenience. Okay, so this particular equation becomes like what? This will be omega square. So if you substitute cos ka is equal to 1 minus 2 sine square ka by 2. This is sine square ka by 2. Okay, so that is you will be getting 2c by m 1 minus 1 plus 2 sine square ka by 2. Okay, so that implies you will be getting the answer as, that implies you will be getting the answer as sorry, so you will be getting omega square is equal to 4c, this 1 minus 1 goes cancel, 4c by m sine square ka by 2. Okay, so this is an important equation, keep it as equation number 2. Okay, and this omega is frequency of vibration, that is already we said that, and this is the omega. It's actually giving the relation between omega and k. You can see omega here, you can see k here, and this relation between omega and k, which is called the dispersion relation. So if there is a relation between omega and k, omega is angular frequency or frequency of vibration of monoatomic lattice, monoatomic lattice. Okay, so which has a dispersion relation, that is omega versus k, and you can see that how omega and k changes with respect to the change in each other. Okay, so that's what you can see here. Okay, so this is the frequency of vibration of monoatomic lattice, frequency of vibration of a monoatomic lattice. What is monoatomic lattice means? The atoms of the crystal is made up of a single type of atom. Okay, single type of atom. So it's a frequency of vibration of monoatomic atom. Now, at this point, we can actually say that lattice vibrations are basically quantized. Okay, so the energy quanta. Okay, you already know that the light has a quantized, and which we call as photon, and here the energy of lattice vibration. So energy quanta of lattice vibration, we call it as phonons. Okay, is called as phonons. Okay, And we also say that when you execute a vibration, in a lattice, so it will frame or it will form a wave. Okay, so the wave that form at the due to lattice vibration, okay, or wave due to the lattice vibration is called elastic wave, which is called as elastic wave. Okay, and phonon, we generally say that which follow Bose-Einstein statistics. You know that photon also follow Bose-Einstein statistics, and photon we consider as a boson particle. And here also we say that phonon, the condensed lattice vibrational energy, we also call as phonons, which is follow Bose-Einstein statistics. Okay, so we can also say that this phonon also you can call as a boson in that case. We know that bosons having a spin value that is 1. Okay, and here when you say that the frequency omega that is equal to the frequency omega, as already we specified, omega square. So if you take it as simply omega, so it will be root 4c by m sine Ka by 2. So you have to take the magnitude of that one. So this you can actually keep it as equation number 3. So here we actually taken the modulus because the frequency should not be negative. Okay, so that's why we have taken sine Ka by 2 as inside the modulus, because frequency may not be negative in any case. Okay, and you can also see that this omega is depends on what, this sine, sorry, depends on sine Ka by 2. So it's actually omega is depends on the wave vector k as well, and where a is the lattice parameter or the distance between two adjacent atom. Okay, so this is a one part of a discussion you can see here. Now you can actually see that you may be familiar that, for example, if I specify omega is equal to a sine Ka by 2, okay, where a means it is actually a constant. Okay, a is a constant. So if you want to find the spring constant here, okay, so you want to find the spring constant. So what will be spring constant? So spring constant, by comparing this particular equation, you can actually say that this will be in the, this will be root to 4c by m. Then means c will be m a square by 4. Okay, so it's a general aspect I just represent. And now if I say that a velocity of sound, a velocity of sound in solid, which is s is equal to ca, okay, then for example we have said that we have vs is the velocity of sound. Okay, so in solid, and s is equal to ca, where s is the stiffness parameter. Okay, or rather you can also say that that is a stiffness of longitudinal stiffness. And if you say that rho is equal to m by a, which you can say that mass density, then the above frequency of vibration equation, okay, particularly sorry, this particular equation So this particular equation will transforming into, like you can see, so it will be, so if I say that Vs, velocity of sound, is equal to root S by rho. Rho is the mass density, S is the stiffness, and you can see that Vs becomes, in that case, it will be root Ca by M by A. Okay, so that you will be getting as A root C by M, where C is the spring constant. Okay, so you can get that Vs is equal to A root C by M, and if you see that 2 Vs means that is A root 4C by M. Okay, so that you can actually change that omega equation in terms of velocity of sound. So it is 2 by A Vs, where Vs is the sound of velocity of sound, sine Ka by 2. So if you consider a sound wave is traveling through a solid, then the corresponding equation of frequency of vibration you can actually connect by using velocity of sound and the wave vector representation, where A is again, as we said, the lattice parameter of that one. And now here we consider some limiting cases or some specific condition. Okay, so by considering the above frequency vibration equation, so you can actually, okay, so let me just discuss about some limiting cases. Okay, so limiting cases means we are actually giving, we are considering the above equation, frequency equation. Okay, so this frequency equation is omega is equal to frequency vibration of a monoatomic lattice, that is root 4c by m sine Ka by 2. So this is our equation, right? So now we see that we have the first condition, that is we have at low frequency. Okay, low frequency, so low frequency means we have a longer wavelength. Okay, so if the frequency is low, that means the wavelength is long one. So for long wavelength, we see that we have a relation like frequency relation, that is already, you know, that nu is equal to c by lambda. Okay, so that's why if the nu increases, if the lambda increases, nu will be very small. Okay, so that's you can see from this equation. And also if k tends to 0, k means the wave vector tends to 0, k means wave vector which is tending to 0, and where k is what, k means that is 2 pi by lambda, 2 pi by lambda. So that is lambda is very high. So lambda very high means k is tending to 0. So for low wavelength, k will be tending to 0. So we can say that sine k by 2, which will be approximated as k by 2 in that scenario. If lambda is very high, then k will be tending to 0. So sine ka by 2 will be tending to ka by 2. So its omega becomes what? It will be 2c by m ka by 2 will become. Okay, so that is omega is equal to root c by m ka will come. Ka. So this is the equation for a longer wavelength at a lower frequency case. Okay, so in that case k is tending to 0, and you can see that importantly here omega is proportional to k. Omega is proportional to k, so that is a linear dependency. So the angular frequencies linearly depend on the wave vector k. So at that scenario, you can actually, the associated phase velocity will be Vp is equal to omega by k. So that is the phase velocity Vp will be what? Omega means that is root c by m a will come. Okay, and that is the velocity of sound. Okay, root c by m a. So that is the velocity of sound will come. And now if you consider group velocity, because the wave will not, phase velocity means the velocity of a single wave, And in group velocity case, you have to take the dw by dk. So see d omega by dk. So Vg becomes, you can see that Vg, the value of Vg also will be C by M A. So it will be Vs. So if you take the derivative of omega with respect to dk, so you can see that the value. So that means Vp is equal to Vg is equal to Vs. So the group velocity is equal to phase velocity is equal to the velocity of sound. So at low frequency, longer wavelength, the medium is non-dispersive. Okay, so the medium, the highlight of this one is, so the medium is non-dispersive. If the phase velocity is equal to group velocity, in that case the medium is non-dispersive. Okay, hence it can be considered as a continuous and homogeneous medium. Okay, so we can, if it is, the medium is non-dispersive means, so the medium is a continuous one and the medium is also a homogeneous medium. So we'll consider one more case. Okay, so we'll consider one more limiting cases. So that is at short wavelength or a smaller wavelength, okay, or high frequency. Okay, high frequency, short wavelength. So in that case, we cannot approximate the value of k. So there will be no approximation for k in that case. So the omega, we have to take it as of. As of means omega c by 4 root 4c by m sin k by 2. So you have to take like as of this term as at short wavelength, high frequency, there will be no approximation. There will be no approximation for k. So that you have to take omega is equal to root 4c by m and sin k by 2. So if you take the phase velocity in that scenario, omega by k, so it will be getting us 1 by k root 4c by m sin ka by 2. And if you take the Vg, that is d omega by dk in that scenario, that you will be getting as a by 2 root 4c by m cos ka by 2. Okay, here because we are actually taking the derivative of omega here, d omega by dk, so you will be getting us this case. And as you can see that at a short wavelength, WL means short wavelength, where Vp is not equal to Vg, Vp not equal to Vg, hence the medium is dispersive. The medium is dispersive. That means if there is a change in omega and wave vector k, so the Vg will be so omega will be also changing with respect to that. So now at what value the k will be 0, sorry, at what value of k, at what value of k you are going to get Vg is equal to 0. So if you want to get Vg is equal to 0, you basically need to get cos ka by 2 should be equal to 0. So how you will be getting cos ka by 2 0? Cos ka by 2 will be 0, you will be getting only plus or minus pi by 2. Okay, so that means k is equal to what? K is equal to plus or minus pi by 2. Okay, so these are the basically the boundary. So this k is equal to plus or minus 2 is a boundary of first Brillouin zone. Okay, so you would have studied the Brillouin zone case in crystal structure of your first module. Okay, so you can see that this k is equal to plus or minus pi by 2 is the first Brillouin, sorry, pi by a, sorry, it's not pi by 2, it will be pi by a, sorry. Okay, so this will be plus or minus pi by a. Okay, so that is the boundary of a first Brillouin zone, and you can see that at Brillouin zone boundary, at Brillouin zone boundary, especially at the first Brillouin zone boundary, like k is equal to plus or minus pi by a, you'll be getting as Vg is equal to 0. Okay, you will be getting as Vg is equal to 0 at a brilliant zone boundary. Okay, and now if in this particular case, if you drop a omega versus k graph, the slope you will be going at as Vg. Okay, so the slope of that particular graph will be Vg. Okay, and you can see that at zone boundary you can actually get, since the Vg is equal to 0, the corresponding graph you are going to get is what? It will be flat. So like you'll be going to get a graph like this. Okay, you can see this one. Okay, so here this one is omega and this one is k. So this is how the graph will be like this. Okay, and this point we say that sorry, starting point, this flat point started, sorry, okay, this is omega, this is k, and this flat point, so here onwards this will be flat. Okay, so this point where it is starting the flat point, so this is minus pi by a and this is plus pi by a, this is k. Okay, so it will be starting the flat curve over here, and this point is the center of brilliant zone. It is the center of brilliant zone. Okay, and this, okay, so this part you can actually get the frequency of vibration corresponding to that. Okay, uh, and this is the point where zone boundary, brilliant zone boundary. So the frequency of band means the allowed frequency which wave can propagate. So this is actually the frequency band. This region we call it as frequency band. This region, okay, this region we call as frequency band. Frequency band means the allowed values of frequency for which a wave can propagate. So beyond this frequency band, wave will not be propagated, or rather you can say that it will be forbidden. So the group velocity at the top of the band is 0. Okay, at this point group velocity will be equal to 0 at this point, and you can also see that the maximum, the omega max will be equal to, you are going to get that 4c by m. So the maximum value is the, you can actually say that that's the top of the band, and this is the point where bottom, and this is top of band means. Okay, so the top of the band omega max is equal to root 4c by m, and you can see that you can see that the approximate value for a monoatomic lattice, okay, for monoatomic lattice, omega max is equal to 10 raised to 14 per second. 10 raised to 14 per second. So monoatomic lattice, lattice will behave as a low pass filter. So it will behave as a low pass filter. That means it will only allow the low frequency waves. Okay. So because the frequency greater than omega max cannot propagate through that band, so frequency lower than omega max can only propagate through that boundary. Okay, so if there is a frequency that is coming above the omega max, so it will allow. So for example, if I can say that if the case of omega is greater than or equal to omega max, So the way which will not allow to propagate through that medium. Okay, so that's all about the discussion of one dimensional vibration of one dimensional monoatomic lattice. So its the main intake was the relation, the uh, frequency of vibration of a monoatomic lattice. So that is, we already said, that is omega is equal to root 4c by m sine ka by 2. Then we consider two limiting cases. One is for a longer wavelength, one is for a shorter wavelength. And for a shorter wavelength, you can see that the Vg will be 0 at k is equal to plus or minus pi by a. So that is called the brilliant zone boundary of first brilliant zone boundary. And you can see that omega max, you can find the maximum frequency it can allowed is this is the point where omega max will come. So that is omega max is this point. Omega max is equal to root 4c by m. So this is the top of the band, and you can see the bottom of the band. So this is the frequency band. Frequency band means only frequency in that in that interval will be only allowed to propagate within that solid. Okay, in that case of monoatomic solid case. So you can see that the omega max will be 10 raised to 14 per second for monoatomic lattice, and which can be considered as a low pass filter because it won't allow the frequency greater than omega max. Okay, so that's the main intake of today. So we just started lattice vibration, and we have discussed about the vibration of a one dimensional monoatomic lattice, and we have identified the frequency, and we have find the frequency of vibration in two limiting cases. And we also discussed about monoatomic lattice can also act as a low pass filter. So with that, I'm just ending today's session. So next session we'll discuss about vibration of a one dimensional diatomic molecule. Okay, so that we'll discuss on the next session. Thank you.